Hello guys, let's have some examples on local backlink problems here. So I have here a problem on the determination of local backlink effect on road shape sections, not particularly wide flange sections. So here we are simply asked to determine the nominal actual compressive strength Pn for W14 by 32 shape, which is of course a standard section. So the properties are given here, and the first thing to do is to check the effect of local backlink. So in this particular problem, we need to have the limits, no? Lambda r that we uh, that we will use to compare, no, the actual. So these are now the limits of the width to thickness ratio lambda r, and these are the actual width to thickness ratio. Okay, so this is the actual lambda. So for the unstiffened element, no, so we are now checking your local backlink to both unstiffened element and the stiffened element. And these stiffened and unstiffened elements simply are the ones uh, that compose your W14 by 32. So this part here becomes your unstiffened element with a width of BF over 2. Okay, so this is now your unstiffened part, and this is the element that represents your stiffened part. Okay, so the unstiffened is actually the overhanging flange or projected flange, and the stiffened part is actually your web. And for the actual values of BF over 2 TF, so we have here the thickness TF and the thickness TW. We simply get the ratio of the actual lambda BF over 2 TF, which is 7.136, and H over TW, which is 9.597. You can also check this from table, no? But if you can compute it, why you don't need to get it from the table. Now, to check the limiting value for lambdas of r, we need to look into our reference, the NSCP or the AISC reference for this. And I have here a part of the table wherein the values of the limits lambda r can be obtained. Okay, so for lambda r, we now refer to case 3. So this is a uniform compression. Always your uniform compression pertains to column problems, while flexural compression pertains to beam problems. No? So later on we will be using these values for beam behavior. Okay, so for uniform compression in flanges of rolled I-shaped sections, okay, flanges rolled, so we need to take the value of 0.56 square root of E over Fy. And for your stiffened part, which is the web, okay, so we can look into case 10, which is again a uniform compression pertaining to a column problem. So this is 1.49 square root of E over Fy. So those are the values that we are going to compare with the actual lambdas. So this is computed to be 0.56 square root of E, which is 29,000 KSI divided by Fy, given to be 50 KSI. So this is 13.487. And for lambdas of R of the a stiffened part, which is the web, we have the 1.49 square root of 29,000 all over 50, which is 35.884. And obviously, since your actual is less than the limit both in both the stiffened and unstiffened section, then we can conclude that your section has not critical for slenderness, and therefore we assume the value of QS and QA to be equal to 1, or simply conclude that there is no local buckling uh, behavior that will occur. Okay, so for your nominal capacity now, we simply proceed with the usual computation of our limits for your lambda, your C sub C. Okay, so this is the limit C sub C, and this is now your actual okay, weak axis buckling. So KL over Ry. So since Ry is the weaker axis, we multiplied by 12 to convert it to inches. We get 47.872 less than 113. Therefore, it's inelastic buckling, and hence, if we consider now your column strength curve, okay, so this is our 113.432, and our actual value for KL over R is 47.8. So our value for FCR falls on the inelastic buckling region, given by the formula FCR is equal to 0.658 Fy over Fe. So this Q, no matter what the value is, will actually take into consideration the local buckling effect. Okay, but since Q is equal to 1.0 here, okay, so your Q is simply equal to QA times QS, which is 1.0. Then this simply reduced to an equation equivalent to the global buckling Fy over Fe times Fy. Okay, so plugging in the values, your FCR now becomes 42.286, and if we multiply it by the area, gross, and the reduction factor Vc, the value of VCPN now becomes 1,477 Newton, or simply 1.477 kilo Newton. So that's it for the local buckling effect on wide flange. So there is actually no no local backlink behavior happening to our W shape. And let's now go to the built-up shape of example 6.19.4, wherein this is again is also an I section composed of plates. Therefore, this is a built-up non-standard I-shaped section. So we use Fy equals 100 KSI and use LRF-DSR method to compute for your nominal actual compressive strength Pn. So the given values are the plate dimensions and the web, the flange and the plate dimensions on the web. Also your Fy is 100 and your KL is simply equal to 10 feet. Okay, so that's I think 10 10 feet effective length. So first we solve for the property. Since this is a non-standard section, we have to deal with the computation of your area and the area, the moment of inertia and the radius of gyration. Of course, the centroid is exactly at the center of geometry, which is this one. And if we compute the area, so we just compute the flanges, and the web. Okay, so the total area now is 12.75, and your Ix is simply equivalent to this formula. So this is actually another way of solving the moment of inertia of an I section. Okay, another method. So I'd like you to study how this was obtained. You can use Varignon's theorem to come up with the moment of inertia also, and check whether the value will match this value here. Okay, so of course this is in inch cube, this is in inch square, and your Iy is simply this one. Okay, so we also use the transfer formula for the moment of inertia to obtain this value in inch cube. So for your Rx and Ry, we simply use the formula square root of Ix over Ag and Iy over Ag. And we check for the local buckling effect by simply comparing your actual lambda Bf over 2f. So this is the flange, this is for the web. No? So the flange is actually for the unstiffened, and the web is for the stiffened part. Okay, so take a look at the comparison. So for a built-up shape, this is actually the more exact comparison for your lambdas of R, since in our table we can very well refer to again to the table here, and take note that we are now dealing with the uniform compression of built-up. Okay, a section, not rolled shape. So this is the more precise value of it, not 0.56. But why did I use 0.56 here? This is just a logical comparison that if your lambdas of R on the basis of this formula you choose, and it is concluded that this is greater than this, then it is more likely that this will be greater than lambdas of R. So this is just a an analysis that a practical analysis that compares a smaller, so this is now a bigger, rather say bigger limit to a smaller limit. So if the bigger limit is exceeded, then it is concluded that the smaller limit will also be exceeded. That's why sometimes you don't need to get Kc. You simply take a look at this formula and compare. If this exceeds, then it is slender. If it does not exceed, then you have to check. It's the time you have to check for the smaller limit. And this is smaller because of the value of Kc that is ranging from 0.35 to 0.76. Okay, so in this particular problem, our value for Kc is 0.603 on the basis of this formula, and hence if you substitute it here, we get now this value. So in either case, I have proven that the actual width to thickness ratio is greater than the limits, therefore both are slender. So Qs is actually less than 1.0. And for your web backlink requirement, again we look into the table. No? So for the web backlink requirement, we note that the value for on case 10 is actually a uniform compression in the webs of all doubly symmetric shape, I shape, whether it is rolled or built up. Okay, so this is applicable to both rolled sections and built up sections. So it's just the same as the problem in the first example. Okay, so this is 1.49 square root of E over Fy, 25, and H over TW. You can get this again. You can also get this from table. Of course, you don't have a table to get it, so you have to compute it. H over TW is equal to 44 greater than 25. Therefore, again, it's slender. Then your QA now is less than 1. Okay, so we need to solve now QS and QA on the basis of the lecture I gave you a while ago. And in order to solve for QS, no, so we simply apply the formula 2A and 2B. So we try formula 2A and 2B on our reference. So where's that for? I think this is the one. 2. Okay, so this is now 2A and 2B, no? So okay, so this is the one, the formula that I'm referring to. We have to apply the use of this formula here and this formula here, and check whether this P over T ratio, or this is the lambda ratio, falls here or it falls in between these two values. Okay, so if it falls here, then QS is equal to 1. If it falls in between, then QS is given by this formula here. And if it is exceeding the value of 1.17, your formula will be a slender formula similar to the format of the Euler formula in your global backlink concept. Okay, so let's now check. So for the value, we actually have solved already this value here, which is 8.463. So your actual BF over T is actually, I think, greater than this, which is 10, no? So if you will look at P over T here, it's actually 10, no? So our value here is of lambda, which is B over 2TF, is 10. So this is greater than this, but less than this. So our formula is in our lambda is in between these two values. Therefore, we use the formula for 2b, which is this one here. So QS now becomes 0.923. So for your QA value, we have to use the analogy on the shape factor QA equal to A effective over AG or A gross. So the computation for this is actually a trial and error solution wherein you have to assume first a value of your f, and f can actually be a good guess, can actually be fy, no? So for conservative results, for this particular problem, I made a guess equivalent to 65, and let's check whether your FCR will actually be very near, okay, to F that was assumed. So the checking is you assume a value of F and then you check FCR if it is very near to your assumed value of F. Okay, so we proceed now with A effective. So the area effective is simply the gross minus the ineffective. So this is now the ineffective area. So the gross area minus the ineffective area will give you the effective area. Here, your B, since we are referring here on the stiffened element, and the stiffened element is actually the web, no? So this is the one that is referred here. So instead of having a B value, we are actually referring to an H value here. So we assume that B is equal to, define B is equal to H. Hence, your B effective now becomes 1.92T. So this is the formula to be used, no? Square root of E over F, 1 minus 0.38. Okay, your B over T now becomes H over TW. No? So this part here becomes H over TW there. So everything is known. So you get your B effect to be 8.289. And your area effective now becomes AG minus B minus PE of, times T is equal to 12.072. You now divide this A effective to the gross area, then you get 0.947. So your Q now, your total Q now becomes the product of QA and QS, which is 0.874. And then we solve your FCR on the basis of the formula for local backlink. So the only difference with this and the global backlink is this value here, no? So take note that Q is always inserted beside FY. So lahat ng may FY, lalagyan mo lang ng Q, okay? So Q is inserted beside Fy. There, you get your C sub C, which is this. Then also in this formula, you have to, not that formula, in this formula you have to insert Q in the Fy there, and also here you insert Q in the Fy to get your final FCR, which is 65. 0.975. So this is very near to our assumed value of f is equal to 65. So you can stop here right now by concluding that your VCPN is equal to VCFCRAG equivalent to 757.061. So in case this is not yet near to your assumed value, then what you're going to do is to plug in or replace your F is equal to your FCR and then recompute QA and QS. Okay, so that is how you do it as in a trial error uh, format. So this procedure is easier done using, of course, a program uh, such as MathCAD. I'll show to you the use of such iteration regarding the trial and error method of on the value of f after this video. Okay, thank you very much for listening.